A radar with a dish antenna can tell us the direction to a contact by just being pointed at it. If you cycle the emitter on and off in pulses, then you can measure the time delay of the echoes to find that target's range. You can even figure out a target's height by its angle above the ground. So this lets us figure out where it's at in 3 dimensions. But is that all? Let's find out how the Doppler effect can tell us more. There's an additional factor that we can track besides azimuth, range, and height. We can also acquire target speed by measuring how much the frequency of our radar changed from the time it left the radar to when it returned. That's because the frequency will shift depending on how fast the target is moving. Anytime radar waves are reflected from a stationary object, they'll return with the same wavelength they started with. But once an object starts moving, then the waves will compress in front of it. This shortens the distance between waves, and we know that a shorter wavelength means a higher frequency. Conversely, it means the waves behind it get longer. Here's an example. An S-band radar can send out waves at a frequency of 2800 MHz. If those waves come back 1 kHz higher, then we know the target is closing with the radar at a speed of 40 meters per second, which is about 80 knots. And if it was 2 kHz higher, then it would be closing at 160 knots. A lower frequency would mean the target is moving away. So if you can measure the difference in frequency, you can determine the target speed. However, there's a caveat. Only the waves in front and behind the moving object have their wavelengths changed. These reflections that are 90 degrees to either side come back at exactly the same wavelength. This means we can only measure the speed towards or away from the emitter. The name for this is radial velocity. That's because it's the movement on these lines that radiate away from our emitter. On its own, a radar with the capability to measure the Doppler effect can take simple speed measurements. In fact, that's exactly how law enforcement radar guns work. That Doppler capability also allows weather researchers to see the speed of various parts of a weather pattern in real time. That lets them identify severe weather like the tornado forming in this image. Whenever a Doppler pattern indicates intense high-speed rotation like this hook we see here, it's a strong sign that a tornado might form there. On its own, this Doppler capability doesn't add much value to airborne radars. But that changed with the advent of digital computers that were small enough to fit inside of a fighter. This happened in the 1970s, ushering in a new era in aerial warfare. The most noteworthy effect is the ability to filter out returns that are moving at the same radial velocity as the Earth's surface. Here's how that would look from the perspective of a mobile radar like what you would find on an aircraft. This big spike is from the main lobe of our radar reflecting off of ground clutter. It's at a higher frequency than what's being transmitted. This is because the aircraft's forward movement is introducing closure with the terrain. So the spike will always be at the aircraft's velocity relative to the terrain. In other words, it will move outward as you speed up and come closer as you slow down. All this back here is ground clutter returns from the side lobes. This includes some rearward-facing side lobes, which is why we have negative frequency returns. If an airborne target is inbound to our radar, we'll see an additional spike here. And if it's outbound, we'll see a spike here. The difference is due to our relative speeds. The outbound target is closer to our own, so naturally its frequency will be closer and show a smaller Doppler shift. Since we're not interested in this ground clutter spike, we want to filter it out of our results. So we can place boundaries around it like this, and anything inside those boundaries won't be displayed. This type of filter is informally known as the notch. As you've probably guessed, this filtering isn't perfect. Any target moving at or near the radial speed as our ground clutter is going to be hidden in the returns that are being filtered out. So when we see a target moving at a lower altitude than our radar, like this fighter moving below the horizon, it won't show up because it's within the Doppler shift range that we're filtering out. But if you notice, this second target at a higher altitude is showing up. We can still see it even though it's at a longer range. That's because the signal processor in our radar is smart enough to only do Doppler filtering when there's ground clutter present. Just remember that this is a feature that needs to be added by the builder, so not every radar will have it. That's not all there is to Doppler radars. Just like how pulse signals have an ambiguity problem, so does Doppler measurement. Instead of being a range problem, With Doppler measurement, it's a frequency problem. Imagine we send out a radar wave at one wavelength like this. Now let's say we're sending out pulses at an interval represented by these lines. We can then measure the reflected waves at these points as well. If the wavelength is slightly shorter, then we can use that to determine the target is moving towards us. But if it gets to an even shorter wavelength that matches our samples like this, then we have a problem. Our receiver can't tell the difference between this shorter wavelength and the wavelength we sent out. In other words, this shorter radar echo looks exactly the same to our receiver as a stationary target. This is an oversimplification, but it illustrates the concept of aliasing. Aliasing happens at a certain combination of wavelength and PRF. But you'll also find aliasing at multiples of this PRF. The radial speeds where this happens are known as blind speeds. Aliasing can also happen if the target is moving the same speed as our emitter. So this is an additional level of masking beyond being hidden in ground clutter. Like with this fighter that's flying ahead of us at the same speed. Because it's flying at one of the blind speeds, it's getting filtered out of our radar display. But watch what happens once we accelerate. Now that we're significantly faster than the target, it shows up on our radar display. There is a solution to these ambiguity challenges. When you increase the pulse repetition frequency, then you take more samples, and then these blind speeds move farther apart. This gives you a broader range to work with. Increasing PRF can help if you have a target with a high radial velocity. But it has a big downside too. Remember that unambiguous range works in the opposite direction. A lower PRF increases that unambiguous range. As you increase PRF to overcome velocity ambiguity, you decrease the maximum unambiguous range. So when it comes to selecting a PRF, you have a trade-off between accurate speed and accurate range. This is called the Doppler dilemma, and it's the reason why there isn't one perfect PRF for all situations. What happens with ambiguous results varies from one system to the next. On one system, the range or velocity shown may jump back and forth between possible results. On another, the contact may just be filtered out entirely. It depends entirely on the builder of the system. In early radars, this could be a significant problem. Those early radars operated at a single frequency with a single PRF, with little or no digital processing capability. But as technology improves, radar systems were introduced that could change these parameters in real time and then do a lot more with the signal echoes they pick up. We'll go over some of these more advanced radars like phased arrays and stealth's interaction with radar in a future video. But this should give you enough to understand the basics of how radars work. I hope you found this video useful and thank you for watching.